Welcome back, everyone, and we're going to continue doing more inverse kinematics and procedural animations. Last video, we kind of start setting up our IK chains, and I think a couple videos ago, we kind of start learning inverse kinematics and using the Fab IK algorithm. Using forwards and backwards. And when we're during that period, I did the two-leg solver. Plus a couple other solvers I put together using Fab IK as as the second stage, where the other two are the first stage. So I actually now kind of redid my two bone solver. Now they're a single stage and doesn't use Fab IK, and I've actually created 3 other solvers that are single pass solvers for inverse kinematics. And today we're going to deal with my second solver, which I'm going to call the circle arc solver. And the premise is that based on the length, the length of the distance from the target determines if you're drawing an arc or practically a full circle. And you kind of see what I mean by it when we start actually visually seeing the code work. But as you see right now, it's doing a curve, and as the points, the two endpoints get closer together, it starts to curve into a circle, and that's why I call it a circle arc IK solver. So it works really well. I've done it like 4 or 5 versions of it, and I finally have a really well working version of it. There probably is simpler ways of going about it, but I'm going to show you how I did it. And the source code will be available to you guys to see and use and learn. And we also have to kind of talk about, because I'm building this built off or from examples from Ubisoft's IK rig system. So the next couple of videos we're going to try to recreate some of those legs, those IK solvers that they kind of demonstrated. Try to replicate them as best as I can just by visually seeing how they work. And I got a lot of the legs working. So, like I said, there's like 4 or 5 legs, and we'll have 4 legs in total by the end of all the videos. So first we're going to talk about the data, because we're going to deal with the whole idea of the system I'm building, which is kind of modeled after Ubisoft, is that you want to have a universal bit of data. And that universal bit of data can then be applied to a solver that then is applied to a specific rig. So here I have like 2 different rigs, and each one has different sets of bones, but I'm doing a single bit of animation. So I'm only doing 1 bit of animation, and that data that this represents gets passed to here and to here, and it just aligns all the bones based on the data. And the idea is the orange dot, if I can zoom in closer, that's essentially the hip. That's the hip. That's the start of our chain, of our IK chain. In the previous video, we start building up our IK chains, and now we're actually going to do the IK part of the chains. And the red dot represents the distance. Like, this is the end target. This is where we want the end of the chain to touch. So anywhere that red dot goes, that's the end of the chain. That's where it wants to go. And the way the solution I came with to make the data where it's reusable is that the first thing you need to determine is the axis direction. So green is forward, red is left and right, and blue is up. So that's what you're seeing here. This is just a direction of rotation. It's just a quaternion. So in this instance, I'm just doing a quaternion rotation, and wherever the forward direction is where the green line is being pointed at. So for when we're doing inverse kinematics, that's ideally what we want. We want to know which direction we want to be pointing at, and then we also want to know where the endpoint is, and that's the red dot. And we determined the red dot by, I came with the solution for me was, since every bone system is going to have different length chains, like right now, these are both equal. They have the exact same distance. They're all like about 1 unit length. But if the one leg is, let's say, 1 unit length and the other leg is 2 unit lengths, how do you animate them together with the exact same data. And my solution is that you don't animate the actual length, and you don't actually animate the actual target. What you literally animate is a scalar value between 0 and 1. So that's what this is. This is doing a scalar value between 0 and 1. I'm animating between those two values. So if I by using that scalar value, I can say, well, how long is this chain? I want to animate it at this scalar value. So it takes the length of the chain, multiplies by the scalar value, then it knows the distance between the hip and the end target. Now, let's say if there's a specific target I want to do, what I would do is then to take the target position, minus from the hip. At that point, I have the direction that I want to go to, and then once I have the direction, I can also say give me the actual length between the 2 points. Once I have the length between the 2 points, I can do that divided by the length of the chain, which gives me the scalar value. And then from there, I can then just apply it. Then at that point, then I have the scalar value, and I have the direction, which is my target data. Then I can pass to the solvers. So if I'm just doing like procedurally animations with no actual IK itself, like I actually have a specific target I'm trying to reach, I can just animate the scale. If there is a specific target I'm trying to reach, like there's like I'm trying to touch a wall, or there's something on the floor I want to reach and touch, like I said, that's how I would go about calculating it. Because like I said, just calculate the distance from the hip to the target, and divide that distance by the total length of the chain. That gives you a scalar value. Now, if the scalar value that results is greater than 1, that means you just extend the chain all the way. So you just extend it to maximum, because at that point you don't need to do any IK at all, really. You just make the chain reach as far as it can, because it's beyond the point. Anything greater than 1 means that target is beyond the range of the chain. So that's the solution I came with, where how I create this universal data that can be applied to all these rigs with different scalars that represent the data. And like I said, it can be animated, and at the same time it can be used as inverse kinematics, so we can actually move things toward actual targets. And we're not using FabIK at all in any of this stuff. All right, so now you got the idea what the data, how the data is laid out, and what this section, because this is like one of the most important things, because all these legs depend on that data. So the circle arc, I tried to do the circle arc a couple different ways, and the final solution is probably the easiest and kind of somewhat more complicated way, but I tried to do arc lengths and everything else. Everything just didn't line up perfectly, and I managed to come up with something. But the solution is simpler, but at the same time comes with a piece that's kind of complicated. But overall, it worked out for me. I'll explain it to you. It's wacky how I went about it. I'm sure there's a much simpler way to do it. So let me illustrate the whole idea of the circle arc algorithm. So we have let's say we have like a target. Like I said, we want to know that scalar value. So we have a point. Let's say that's the start of our chain, and this is the end of our chain. So this is let's say this is one chain unit. Like I don't know how long the chain is, so that's one chain unit. And let's say I want to animate half of it. So when the unit is the scalar value is 1, the chain is straight across. But let's say if I want half of that chain unit, so let's pretend that's half, and there's the other half. All right. So this is my actual target. This is where I want to get to. So even though the chain is this long, I want to go here. So the idea is that I want to turn this chain into an arc. But if the line, let's say if the point between the two is really, really close, I don't want to make an arc. I actually want to do almost a circle, which is considered an arc. If you don't do a complete circle, and then it's an arc. So that's so the idea is that we go from a completely straight line to an arc to a circle. Okay, so based on that scalar value, like how the distance between the 2 points, we can take that scalar value times pi times 2. That's pi times 2 is 360 degrees. So if I say I want, let's say this is half, that equals, divided by half, whatever. This would create about 180 degree arc. So the arc will be half a circle. All right? So we got a half a degree. That's great. So, and one of without using circle arcs or anything else, one very simple solution is how many bones do you have? Let's say if we have 6 bones, and we just take 180 degrees and divide it by 6. So this way, I don't know what it is. It's whatever that value is. It's whatever that is. Can I do it in my head? 40. Wait, 6 times 6. No, it's 4 times 6, right? Makes 18. So it's 40 degrees. So 40 degrees, I take it. I might be doing the math wrong in my head, but let's just say I'm right, and it's 40 degrees. So that means I rotate each bone by 40 degrees. So I have the first bone, I say that's 40 degrees. The next bone, I say 40 degrees. Next bone, 40 degrees. Next bone, 40 degrees, so forth and so forth. And if it was an ideal world, this would be perfect. But it's not, even though this does take us part of the way there. Now, the problem with doing this is that I end up overshooting or undershooting my target. So let's say I'm trying to do an 180 degree bone thing. When I do that 40 degrees, I might end up doing this. That's where I want to be. This is where I end up. So I got the arc just right. It looks beautiful. It's everything perfectly divided, but it's missing its target. That the whole point of inverse kinematic is to reach its target, and that's a problem. So how do I get to do that? So what I want to do is I did a lot of trial and error and try to figure out which parts of the code I can maybe do an offset with, and the only thing I can find is the angle. So remember when we said that, okay, we have an 180 degree angle, that's what we're trying to implement. I try to create an offset. So I end up calculating 180 degrees total. That's the arc I want to draw. But I want to subtract by some offset. That creates a new angle, which then I can divide by my bones, right? So if I do by adding in some kind of offset, that 180 degree angle becomes a slightly less angle, but then I end up actually hitting my target. But now, okay, so like I said, I pick 180 degrees. I calculated my offset. I just randomly just subtracted until I reached my target, and that worked. Then I tried a different angle, and that offset didn't work. So what I end up doing is trial and error, which created I went at the basic trial and error. Let's say I started at 25%, 50%, 75%, then 85%. It's like I end up creating like points of data. So as I tried every single degree and then try to create an offset for every specific degree, I end up creating a bit of curved data that looks like this. Right? And that ended up being the curve of the offset, which kind of caused a problem. Because the curve is actually really wacky, because like I said, I use Desmos to help me solve that offset problem. Oops. I don't know why it's doing that. All right. So as you can see, the points, like I said, this is... I think maybe 10%. Yeah, that's 10%. This is 25%. This should be about 50%, and then I got as I got higher, like I kind of did a round. Like I did like 75%. Then I noticed that things were different, so I ended up incrementing it even smaller. So basically, I had all these dots or the data points I ended up creating, trying to calculate all the offsets at all these different angles. Then I plotted the points, and when I plot the points, I noticed that it's a very odd curve, and it's like so I couldn't just create it. So the idea was, let me use Desmos, and they have like this nice example of Bezier curve, and I would just kind of use this Bezier curve and just figure out. You just sit there and just manually play with it. Basically, I'm trying to do curve fitting. So I have all this data. I'm trying to fit a curve on the data as closely as I possibly can to try to create a curve that hits all the data points just right. And like I said, I did come with a good one that does a pretty decent job. Like 1 point is slightly off, but in terms of inverse kinematics, you don't need to be absolutely perfect. You just need to be a very good I can't say that word. It sucks having English as a second language, but very approximate. That sounds like it. Approximation. Try to get very close. Try to get as close as possible to the actual value without being exact. That's what I'm trying to convey here. So I can say the word convey. I can't say approximate. Approximate. There you go. I think that's how I say it. Approximate. Approximation, whatever. So I end up creating a function, but of a Bezier curve. By all you have to do is save these two control points. Like these two control points are static, so it starts at 0 over here and ends at 1, so it becomes a scale. The only problem is that I have to go searching for the data. So if I'm at, let's say, I want 1/2 of the angle, I actually have to do let's say at 25% would actually be better. I have to go into my Bezier curve and do a binary search. So I say at 0.5, I'm here. Take that 0.5 and apply it to the x scale of a Bezier curve, because I'm going to use a 2D Bezier curve. And that 0.5 says, okay, this is the x value, but that's not the x value I'm looking for. So I compare it to see, is it left or right? And if it's less than, I take this point and the half point and then end up calculating the center of that. So it'd be end up 25%. And from there, I was like, okay, is this close to the point? And I just keep repeating that process until I get really close to the t value that represents the scalar value that I'm trying to get for the angle. Once I have that angle that I'm currently trying to get to, like, because I'm trying to get an angle and the offset that belongs to it. So the angle I'm trying to find that angle on the curve, on the x-axis. Once I find that angle on the x-axis, I can take that t value and then do the y version of it. And when I get the y version, it gives me the actual point of offset for that specific angle. So like I said, every angle has its own very unique offset. And that's how I end up solving to move the points exactly where they need to be. So I end up getting that perfect arc, trying to get that perfect arc from start to finish, but try to keep it like simple. So that's only the tricky part. And the function I wrote is a simple binary search. If you ever done a binary search before, it's pretty simple. And binary searches are limited in the sense that everything has to be in order, which makes it easy because the x is in order already. It goes from 0 to 1, so it's easy to kind of just cut something in half and say, is this less than or greater than, and then just cut that section in half and then go forward. Another thing is you can't do things like this. You can't have curves that cross-intersect, because that means two values. There's two x values in the curve, and that's a problem. So you can't do a binary search when you have a curve like that. So as long as all your data is a nice non-concaved, I think that's the word, concave, or like I said, as long as it doesn't intersect each other, you're good to go. And your points one endpoint has to have an x value of 0 and the other end has an x value of 1. So those are the limitations if you want to use a Bezier curve in this fashion to kind of like make there's tools like I think in Unity that kind of does this. So you have like the curve editor. So that's what I'm essentially doing, using the curve. I'm kind of half-assing a curve editor to get the values where I want them to be. So it's a very manual, mathematical way of doing the curve editor. Like I said, I plotted the points, and I'm using this tool to kind of help me. And then once I have the data, it's like these, like I said, these are static points for me. So the only thing is I need to know is that point and that point. So by applying those, saving those 4 values, I can put them in my Bezier curve function plus the x value that I'm looking for, and then it spits out the y value, and then voila, I have a pretty cool, very curvy way to do scale values between 0 and 1. So with that problem solved, now I have one last problem to deal with. So once I did that curvature, that's my endpoint, I ended up getting something like this half the time. It's the right angle. Everything's right except it's curved past the point or above the point. So I still end up overshooting it just by a little. But the solution is actually pretty easy. So I know from here to here, right? The start point and my target, and this is where my new end target is for the curve after I'm done creating it. All I have to do is figure out the angle between these two lines and say and I tell the bone that starts the curve, say subtract that angle, and voila, everything lines up. So like I said, there's the offset was an issue that needed a kind of a complicated solution for it. But when the second problem, which is like a slight offset, it's very easy. Like I said, just get the angle between the target, between the target that we want to get to and the target we're currently at, and literally just subtract. But since we're doing quintorians, it's a little more complicated than just subtracting. With quintorians, let's say we figure out the angle between the two, and the way you do the angle between the two is that you have this angle. Let's say this is angle B, and this is, or let's say rotation B, and this is rotation A. So you have to say B times invert of A. So you have to multiply the invert of A. So that's how you basically subtract. It gives you that angle of rotation between the 2 points. So that gives you, let's say, C. And then you have to have your bone B1. Fine, but the bone rotation, right? The bone itself, the first bone in the chain, has a rotation. So that rotation times invert of C, and that moves this to that spot, to that line, so they all line up perfectly with each other. So that's the entire algorithm of how to get a circle arc. So hopefully you understand that. Like, I know that's a lot of, I guess, a little bit of math or whatever, and it's just a lot of theory. But now we get to look at some code. All right. So we're gonna have a new file called solverarc.html, and you also need to just, if you go into the full fungi.mod folder, there's a couple of new files in there. There is the IK chain animator, which is the same animator I made a couple of videos ago when we were doing procedural walking, except I just fixed it up to work with chains. So I'm not really going to explain the animator, and that's just for the demo file. But for the actual arc file, we're not going to do any kind of animations. I have the arc IK chain solver, but this one's a cleaned up version of it. This file here has the second to last version before I did a final optimization to it. And that's what we're going to look at. We're going to look at the optimized version of it to really get a sense of it. This is a lot of the same code from the last video, dealing with building up our arcade chains. So, we still have our tentacle rig. We still have our pose chain. So, because essentially we're using our solver to create a pose, and then we apply that pose to our chain. So this kind of continues on like from the last video, because we ended it with dealing with poses. Just quickly generate some poses and then apply it, and then we can alert between poses. So that's what we're doing. We're doing that. And here's our data IK targets, and we're gonna put 2 points. That's our starting point, and that's our end point. So we're actually picking a specific spot in space that we want to reach. And I have a debug so I can actually see it. We call our circle arc solver. We pass in our chain. We pass in the target data. We pass in a reference to a pose. So this way it saves all the data to the pose. And then once we have our pose, we apply it to our chain. So this way, I wanted to keep it separately because, like I said, maybe I wanted to do some weird things after the fact. Okay, and yeah. So first, let's look at the IK target, because that's a new one. I have it inside the IK chain solver. Also have transform data, but we'll look at that a little later. So here's our IK target, and that's all. There's not really much to it. We have our rotation. So the rotation is what quaternion is needed to point at the direction that we're getting to. That's what we want. Position is just the world position of the target. I have this here mostly so I can use it with forward kinematics, but not forward kinematics. IK, Fab IK. So I don't think I'm really using this one too much. Even though I do apply it. Scale is also optional. This is when I want to animate it. So I want to set a value between 0 and 1. But when it's null, I'll end up using position to help calculate the scale. So like I said, I think actually I am using that for this video. So we're going to call set end position. And we're going to put point A and point B, and optional what up is, but we don't need to, because we're going to just calculate up first. Let the function calculate up by itself. So we're going to save point B into position, because that's the end target position. That's the end target we're trying to get to. We say scale equals 0 because we don't know what the scale is, because we're not animating scale. We're actually trying to do an IK. Do some simple subtraction, try to get the forward direction. If up direction is not given to us, we just calculate it. We just try to see if z is near 0. If it's near 0, we want the up to be the back direction. Or no. Yeah, if it's near 0, we then have to do another check to see, do we want to use the back or do we want to use the forward as the up direction. If it's not near 0, that means our up direction and our forward direction isn't the same. Then we're going to use the world up direction. So that's really because you can't do a cross product when both vertices are pointing in the same direction. So we know what our forward direction, but we need to figure out what our up direction is. So once we have an up direction, we can then normalize our z, use our up, do a cross product. We normalize it. That becomes our x-axis. Then we take our z-axis, which is our forward, and our x becomes our left, right? And then we do our z and we do our y together. We normalize it. That makes our up. And then once I have that, I have a new function I put, I think, in quaternions. That I can just, it's another function that's like, I think, that I kind of took, and I took it apart and just took out pieces of it, which all I have to do is just pass in the three axes, and it creates a rotation for me. So actually, I think it's the look at function. I took it apart because it does this already, but then it does something else. So the second part I took out and just made a new function with the first part. So this way I can make a quick rotation of it, because a lot of times I need the actual rotation of the direction of the target. So might as well just pre-calculate it for my function, so my functions don't need to do it themselves. Because like I said, I think every single solver ends up needing it anyway that I created. So it's like might as well make the target object actually generate it for me, so I don't have to do it for every single solver. The other function I have is when we're doing animating. So if I'm actually just animating, I'll pass in the quantorian, and I pass in the scalar value. I set position to 0 because there's no end target. I'm not looking for an end target. I'm actually just animating it by scale, and then since I have a quantorian, I just multiply that with the world up. Like the up becomes forward because the bones are pointing up. So this allows me to create the exact axis of rotation that I need, essentially. Even though it looks a little weird that I'm using the up position to calculate the front, back becomes up, and then left becomes left and right. But it works, trust me. It's because, like I said, because the bone is looking up, but the forward direction is its side faces. So I kind of need to compensate for it. It's kind of like creating an offset. So I needed to, even though the bone is here, the forward is here, I'm just changing the forward direction in the direction that the actual bone is rendering. Because the bone renders up because it's pointed up. So that's all I'm really doing. And then again, I just create that rotation based on the axes that I actually have. Because that quantorian, even though it works, doesn't work well for the data. So everything has to be just right. And I have a debug function that allows me to visually see the axis, of which is in that demo. That's where I'm actually creating the debug. So that's the target, that's the end. So now we have the end data all calculated, all working just fine. Now we got to do the arc solver. So here's the Bezier curve. The 2 points, the middle, the control points really, and that's it. Like I said, I made it a constant. That's what I use for it. Here I check to see if the scale is greater than 1. Like I say, if I'm not using scale at all, it'd just be null. It wouldn't work. But if the scale equals to 1, I call a function called full direction. And full direction, and it returns, is, like I said, all it does is straighten out the chain and point it at that direction. And that direction is that rotation function I said I created right here. When I create that rotation, that's the rotation I use to figure out how to rotate the bone. So I just rotate the first bone by that, and call it a day, really. I could probably show you full direction. And this, like I said, this is what all full direction is. It uses the aim direction. And the aim direction is just that target rotation. So the first bone gets that target rotation, and I have like an extra offset if I needed to, but it's turned off by default. I only need to turn it on when I need it for specific cases. And I have something called reset position, because if I'm using, there's a certain solver that does positioning instead of rotation, so I need to reset positioning. So that's all it does. It aims the first bone at the target and then resets all the rotation back to the initial rotation that the bone was set to originally, and the initial position that the bone was set to originally. So that's what full direction is, and that's what aim direction is. That's all it does. Very simple. It just like I said, once the 2 endpoints, once the distance is too far away for the chain to reach it, like I say, all you do is just stretch it out. So that's this part. All right, so now we need to get the world position of where the chain starts. So that's the orange point. It's this file. So I need to get that orange point. So we just call our T node. I think I made this brand new. Components, transform nodes, because remember now all our bones are now entities. So now I can actually just use the functionality that's built into the entity for transforms. it's really the same function as get world transform, except I probably took some pieces out. So this way, the only thing I return back is the world position. So that's the function. I really don't explain it. It just goes back and then calculates the world position based on all its parents' rotation transforms. I don't know why I did that. All right, so that's that. Just in case people try like, why am I doing that? But that's that. Check for scale. If the scale is not there, I need to figure out the scale. Okay, so I still need the scale, but like I said, since I'm reaching a target, I'm going to calculate the scale myself. And then I do another check yet again if it's overextended, because now I know what the scale value is. And like, why am I doing it twice? Because if I'm animating by scale and I reach close to or greater than 1, I don't want to have to do this. Like, at least this point, I don't want to calculate my my world position, because if I know my scale is already past 1, there's no point in me doing that. So that's the reason why I haven't done it twice. If I have to calculate my own scale, then I do it again. So it's just an optimization thing. Like I said, at this point, if I reach this point, I'm not animating scale. I'm actually trying to reach a target. Once I got the actual scale, I just invert it, make it a negative, and multiply it by pi2. That gives me the angle. This is where I apply the offset, but I'm going to leave the offset for now so you can kind of see how things look like. Then over here I have the transform data. I'll quickly talk about that. Like I said, it's the same thing as the transform node, but it's a more simplified version of it. It's the whole point of my transform data is to this is all it is just 3 things. It's just so I can quickly calculate the world position of things by using transform data. That's it. I wanted something quick and simple that I can have more control over, because I don't want to, like, this has a certain purpose, the transform node. This is a component for entity, but I want to do just some simple math, and I don't want to have all that entity stuff to deal with. I don't want to mix them together. They're the exact same thing. So this ends up being like a copy, but a more streamlined, simple version of the transform node. But the only difference between here, it doesn't actually do anything. I have to do an add. So transform data is kind of like dealing with like making a matrix without making a matrix. So this way, all I do is just say, here's my rotation, here's my position, here's my scale for the next bone, just add to the transform. So it just allows me to just add transform data together. That's all this function is for, or this class. It's a very, very, very simple thing. It's just, like I said, it's just for adding up transforms. And the only reason why I'm doing it here is because I think it at the time was efficient to calculate the world position as I'm calculating the rotation position for each bone. And it's great for debugging, but in the final version, I actually take all this out. But I'll explain to it and I'll show you the final version. So for every bone, I'm trying to calculate its endpoint. Like when the bone is done rotating, where does it point to? What's the endpoint of that bone touching? So we get to see it. The count, I instead of using the chain or post count, I did it minimum because I was thinking maybe at some point I might have some kind of solver or do something where I want to, let's say I might have a chain of like 50, but I only want to apply the first maybe 10 to a specific solver. So this way the pose data might be 10 and the chain might be 50. So whichever one is the smallest is the actual count I'm going to be using. So that's why I'm doing this, because I'm thinking in the future that I might actually have uneven values. So like I only want to do I might want to do a subset of a chain and apply a solver to it. I don't know if I'm going to, but in my head I think I might too. I just don't have a scenario yet. So I'm kind of preparing for a scenario that I don't know. But like I said, this is like a simple fix. If I ever want to, I can just take out the min and whatever. But yeah. So that's why I'm doing that. If you don't understand why I'm trying to do a minimal for future scenario that I'm not sure of yet. So once we have our angle, like I said, I inverted it again with just changing its sign and dividing it by count. So this way, when I said 180 degrees divided by 6, that gives you like 40 or something. That's what I'm doing. So I got that 40 degrees basically. So now I need to figure out the angle for the first bone is different from the angle for every bone afterwards. So the first bone has to be a little extra work. So I create a quaternion rotation using the x-axis of our target data, right? And this is the angle I want to be at. So once I have that rotation, I take the copy of a rotation for our bone, the target rotation I copy to the first bone, then I multiply it by our angle. So I'm making that bone point at A, then I'm trying to make it point. Might be better off drawing a new one. So the idea is for the first bone. I suck at drawing with this old tablet. So for the first bone, I'm going to make it point, or I'm going to give it the rotation that takes me to this point. So now the bone points here. But I know that the rotation for the first bone is here. So I end up multiplying that increment by using a p-mul. So it means it's like it does it backwards, and it then rotates this point to this point. So now it's pointing at the right direction because it kind of rotates the bone a little bit and then points it. So it makes sure that the bone forward direction is pointing at the target. Because if the bone is facing the direction, that's the first bone is pointing in that direction. Every other bone will then use that as the parent value. That means every bone afterwards, I can use the world space x position. Because since the first bone rotates every child bone toward the target, like I said, it rotates every sub bone that doesn't need that rotation. It just you can use the world rotation of x. Hopefully that makes sense to you. So we end up doing that a lot because we got to rotate the first bone toward it, and then every sub bone afterwards doesn't need to have that exact rotation. So that's what I said. So once I multiply, so I end up moving it into the arc, trying to align it up to the arc. I just start start creating the transformation data, so I can find the point of every bone. I reset it again, that increment, by using the same angle of increment, but instead of using target X, I'm using the world X. Because like I said, every bone afterwards is going to take the parent's rotation into a consideration. So it's the parent's rotation that points to the bone plus the rotation of X within aligns it into the arc. So yeah. Hopefully I'm explaining it correctly. Hopefully you can kind of illustrate. Like I said, you have I don't know how to visually do it. So like I said, you have I don't know if I'm spending too much time. So let's say I want to point my thumb at you like this. So that's my parent bone, right? Yeah, so that's what I'm doing. I'm taking the parent bone and I'm pointing it this way. But you remember, it's a parent bone. So that means when I move this bone, the child bone goes with it. Yeah, it's hard to do it. Yeah. Maybe, yeah, something like, I don't know. The camera's like mirror image for me, so it's kind of hard to tell. So yeah, I want to make it look at you, and then as you can see, my index finger now points at you, because no matter which direction I am at, based on my hand movement, X position for this finger is always the same. It's that first bone that changes the rotation. So sorry for that, but I'm trying to figure out some visual ways to you understand of why I'm doing this, because it might not make sense. Like, why am I adding this weird rotation to the first bone, but then every other bone uses world space direction? That's, like I said, it's the first bone that dictates the actual direction, and then every other bone doesn't need to follow suit, follows along. It just follows along the first bone. It's the leader of the pack. You know, it's like a flock of birds. When the first bird that flies in the flock turns, everyone just follows along with it. But every other bird kind of has its own little direction itself. All right. So once we have that angle of rotation, for every sub bone, that we just copy it. It's just copying it. We're not doing any math at all at this point. We're just saving that increment to every single bone. And like I said, this, all it does is just adds up my transform data, so this way I can kind of visually see a red dot of where all the bones are. And this just ends up calculating the final point on the bones. So if I were to go here, and then we go to the actual solver arc file, so as you can see, this bone rotates toward the red dot, and then every single bone has an X. And that's what the transform data is doing. It's calculating the endpoints of every bone. And hopefully you can see it. It's like, that's the green, that's the forward, that's transform X, blue is transform Y. And as you can see, like I said, this is without doing the offset. I overshoot the target. So that's my target. That's my one length. It's just wrong. So if I were to add the offset from that Bezier curve that I showed you earlier, refresh. Now you might be like, well, it's still wrong. No, it's not. It's actually aligned perfectly. It's just the first bone is at the wrong angle. So that bone is at the wrong angle. So, like I said before, all we have to do, so I have that dot and I have that blue dot. What I need to do is find the angle between them and subtract the angle to move that blue dot into that red dot space. And I keep going back to the wrong thing. And I have a function called align forward rotation. It's inside the IK chain solver. It's just and it does exactly that. It align forward rotation. You pass in the chain, you pass in your target, you pass your pose, and you say from what direction. What direction is it? And to do it, like I said, I have to figure out what that blue dot is. That blue dot. So this is what I'm doing, is basically calculating the blue dot. Then I'm normalizing because that's the direction toward the blue dot. Okay? So I already know what the red dot is because that's inside target. What I'm actually, in the end up calculating is the direction from the orange dot, which if you can tell, to the blue dot, which is over here. Then let's go over here. So what I need is that rotation, which this takes you to the red dot. I get the inverse, which is my Q rotation. Create a rotation based on the direction of the endpoint. So I need to create the rotation to the blue dot. Once I have the rotation to the blue dot, since Q target's already inverted, it's the red dot rotation but inverted. I just have to multiply it from the end position, the blue dot's this is the blue dots rotation. This is red dots inverted rotation. Once I multiply it, then I invert it, and then I can then take the rotation that currently exists in the first bone and basically subtract it. So then once it's subtracted, I click refresh. Now it's practically, like I said, I could probably do a better job of setting up all the data points and spend more time getting the curve, so I can get the approximate value much closer. If I spend a lot more time and maybe write some code to actually get like as perfect as possible, since I kind of did everything kind of just hacking away at it, it's not, like I said, it's not going to be perfectly, but it's very, very close. It does touch the red dot. You know, like I said, it's not absolute perfect, but it still gets there. Like if I was trying to reach for a cube, and the cube is going to be bigger than that tiny little dot, I still reach that cube. It doesn't matter if it's exactly perfect. You know, it's as long as I get there, that's all that matters. You know, we're not building a rocket. You know, we're just trying to simulate inverse kinematics. That's all we're doing. And there you go. And that is the circle arc. You know, so like I said, that's the end target, that's direction, that's everything we wanted, and we got everything lined up just about right. And like I said, black dots is all the debugging. So these are all the points that they were. And this is after we do that forward alignment, this is where the bones actually end up at the very end. And that's the circle arc. And if you want to have fun, if I scroll to the top, yeah, that's everything, right? Everything is in here too. And also, like I said, if I wanted to show you how I did it, like I said, this is how I did it. I made I end up calculating all these points based on, you know, it's like I want to say I want 0.1 scalar value, and this is the offset I end up manually figuring out that's close to the dot. And like I said, I did it at 25%. I end up calculating with 25%. I did 5%. I just kept going up and up and up. And as further got up, I started to realize the data was different. So I ended up doing more increments near the, like, getting closer to 1.0, you know, the scale value of 1. And I started noticing that, like, it goes up and it kind of plateaus at 85 and then starts to go down. So that's why I started to increment values in odd ways. So, like I said, it was kind of like a manual process to figure out the points. And then, like I said, I plotted them, and then I did a curve fitting. So this is, like I said, my third attempt. And this is the original function. So, and I guess I'll let you quickly look at what the final optimized version is. So I ended up creating a function called endChainPosition. And this calculates the end position of the chain by creating the transform. So this way, that part of the code is no longer part of circle arc, which makes it a lot simpler. So like the function looks almost the same. All of this part is always the exact same. But that part that we end up calculating and setting the bones, now it's a lot simpler. All that transform stuff is gone. All that debugging stuff is gone. It's a lot more simpler. Like I said, the first bone still needs to kind of be rotated in the right direction and everything else. Yeah. I can probably get rid of this, to be honest, I think. Because if I'm doing a realignment, I'm kind of wasting my time adding that to it. Like I can probably, like I think for optimization, like since I'm doing an alignment, I can actually probably do that. I'm just curious. Let's see. Can I optimize this a little bit more? If I take this out, like I probably can get rid of that. Like I probably don't even need that. No, I don't. Because like I said, I'm already realigning it anyway. So like I said, that's like just part of a code that was there until I figured out I had to realign. Like that was like problem 1. I solved problem 1. And then when I came here, I saw there's a problem 2. So you don't even, like I said, this line of code, you don't even need because the realignment would actually align you anyway. So this is kind of a waste of time. So you really don't need that part. So you just copy the rotation. So this way everything's pointing toward it, and then the first bone gets fixed up during the alignment function. So yeah, so like I said, all that transform is now done here. I do get the end position of the chain. I get the end position, and then end position minus chain position, which is the start of the chain. Again, it's normalized, and then I apply it to the align format. So I really should get rid of this. Again, it's not needed. It's actually not, like, I actually fixed this video, fixed this function during this video. Like, I don't need that. I was like, now I'm like doing this. Like, I don't need that because the realignment fixes it. Why do that to the first bone when it never really aligns correctly anyway? All right, so I click on save. So we can go up here, and I'm going to uncomment this bit of code. Click save, refresh. And there you go. So the target goes over and it straightens out. It calls that full, what is it called? What did I call it? Full something? Full direction. It calls full direction, and that's when it flattens it out. And as you can see, the closer the target gets to the base of the chain, it goes from an arc to a circle. And that black dots, you kind of see where all the points are before they get realigned to the target axis. And you might be, some people might say, well, okay, you created an offset that works, but it probably doesn't work for all bones, or like the amount of bones. And that's the beauty thing. Apparently, the offsets work. So if I were to go here and say the tentacle rig, I want to do, I don't know, make up a number, 14. Refresh. There you go. Those offset, that Bezier curve offset still works pretty well. Do 18 points. So like I said, I did all this kind of complicated thing with the Bezier curve, and end up mathematically working out for me. So like there might be an easier way to do this. But like I said, I tried using arc lengths and it just didn't work. I could get close to it, but everything would kind of start falling apart. This was the only way I was able to actually do it and have the arc be perfect. Like, I want the arc and the circle to be perfect as possible. And this is the only way I can kind of come up with it. As you can see, it does a really good job. And you might be like, why isn't it straightening out? Because I have a defined length in the animation. I have a length of 2, I believe. Yeah, a length of 2. So if I want to do maybe a length of 4, refresh, then it'll straighten out a little bit more. But yeah, look at that. That's circle arc IK solver. So let's go back to 2. Let's try with 3 bones. How well does it work? I don't think I tried anything less. I don't know. Does the target go? So yeah, 3 bones. It probably works for 1 bone, but it's overkill for 1 bone. It should work for 2 bones, but it's overkill for 2 bones. Yeah, it works. I'd rather use my 2-bone solver, but like I said, circle arc works pretty well. There you go. And there you go. You have a circle arc IK solver. There was a guy on YouTube that apparently he kind of made one in Unity, but he was like 8 years ago, and he just demoed it, but he never really showed anyone how to do it. The only clue he had was he used inverse sine cardinal. I tried to research that mathematical thing. I couldn't find anything related to making circle arcs with it at all. If you're watching this video, if you know a simpler way to do this, because apparently you figured it out, please share it, man. It's really cool. Like I said, if you have a better way to approach this to make this arc with a lot less, like without even the Bezier curve offsets, that would be great. Like, if I can get as more accurate with the least amount of math, the better. But like I said, if you like, I kind of want the arc because, like I said, we're working toward building an IK rig, and a lot of spines are 3 to 4 bones long. So if I want to curve the spine of a character, I need to curve it. So that's why I built a solver, because I want to arc a body. I might also want to do like tentacles. So I want to build like a spider bot, and I want to do. I'm gonna use like just two bone solvers to start with the spider bot. Then I kind of want to be able, because I'm going to use this target data, and I want to be able to kind of replace it with tentacle bones. So this way I can use the arc to create the tentacle bone. So this way I can kind of do like a Zelda guardian. So that's what this solver is kind of for. It's really for the spine, for my IK rigs. And then if I want to do some fun stuff with like spider robots, or like some kind of like quadruped robots that's kind of had these like tentacle legs, this solver would be great because it gives that nice arc where the leg can stretch out, then land, and then arc perfectly when it moves closer to the body. It makes a nice arc to a nice circle. So yeah, there you go, circle arc, and that ends up the second bone, the second leg out of the 4 that I'm using to recreate IK rigs. I probably made this video really long. Oh, it's an hour long. Oh shit. So this is probably one of the more complicated of all the bones I've done, or all the IK solvers I've done. This one took me, I think, over a week to do. Oh yeah. I don't know if I can't remember if in the visit video I showed you in the maths file that's in the fungi folder. What the hell? Did I fold it out? That's why I can't see it. I probably folded it out. Constants. Oh, Bezier curve. Yeah, this, I don't remember if I showed you guys this yet. If I did, I'm sorry. But this is the Bezier curve easing function. This is the one that I pop in the target X I'm looking for, the first control, the start of the Bezier curve, the end of the Bezier curve, and the 2 control points. And like I said, I do a binary search. This is my binary search. Then it gets the X position. Then I check to see if it's within the margin of error, which is margin, for me, like if I can get close to this distance, that's as a close of approximation that I want. I can try to make it more accurate the closer you get, but this one gave me a good value when I would sit there and animating and playing around with it. So this is good because I don't want it to be like I said, I don't need it to be absolutely perfect. As long as I want it to be close enough. That's what my goal was. Just get it close enough. I'm not smart enough in math to make it perfect. I'm just not. I just know enough to be dangerous. That's about it. And like I said, it's and if X is great, like, and this determines the next loop. Am I going to go A or B? But if it's within margin, it just breaks. That means I know what my t value is. Then I apply that t value to the exact same Bezier curve math, but on the y, and that gives me the final y value. So if you're looking for it, it'll be in the fungi folder. It'll be in the maths. It's in the section I call curves, and I call it cubic Bezier easing. So it's like an easing. So it's like I said, I can start doing maybe some Bezier curves for animations. So this function will probably help me out a lot in the future. If you have a better Bezier, there are some 1D ones, but they are, like, I found some other ones, but they limit the control points. And I needed the 2 control points to be unlimited. They can be anywhere. I found some good ones. I think maybe it's this one. You can move the control points, but they have to be within the boundaries of 0 and 1. like I said, for what I need them to be anywhere. They can, like I said, the 1 point is like up, really away. So that's why I had to create this function, because the only means of getting that Binder curve just right in 2D, and between 0 and 1 was to kind of make this, which kind of does like a binary search. So it just searches that curve for x. Once it finds x, it gives you y. And x is between 0 and 1. That's about it. So, yeah. So ended here. Sorry for the video being a little bit long, but there's a lot of math. There's a lot to explain. I tried asking people for a lot of help, but no one could help me with this. So that's why it took me so long to make this. But I'm just really happy that I managed to find a way there. It's probably not the best way there, but it's there. So again, like I said, if you or you know someone who's really good at math and they can come up with a better solution of providing an accurate way to create rotations for bones, for IK, that'd be great, to create like circles and arcs. Other than that, please like and subscribe. It helps the channel out. If you like what I'm doing, like again, all the source code's on GitHub. It's free. I don't like people asking for what license to use. I don't know. I don't care. If I put anything on GitHub, that means I really don't care. You guys can just use it whatever you want. There's not, like I said, there's not really much information about IK solvers online. This kind of information, like to do things like this, is if people do know how to do it, they don't share it. that's like I spent so much time on Google trying to find solvers for specific things. There are instances that people know how to do it, they just don't share. And that's fine. It's a lot of work to actually figure this crap out. And if you want to get money from it, by selling it, by all means, your work, you deserve it. But for me, I'm an open source kind of guy. So open source it. I think the more people that know how to do this, the more of this we'll have. That's what I want. This is what I really want. The more people that know how to do this, the better chance that we'll have better versions of this stuff that all of us can use. Because the more efficient, the better these things can be, the more we can do. Like I said, the more great solvers, the more things like an artist can then turn around and make some really amazing stuff. It's like it's hard to procedurally animate a tentacle. It really is. If I make now this arc function will make it easy for anyone to kind of procedurally animate it. Now you have artists and developers and game developers that may be able to easily do certain things that only the big pros that have teams of 20 people, whatever, can figure out. I don't know. I'm just rambling because it's like I'm so passionate about code. It's like I'm passionate about code and sharing. It's like because to me it's the collective. If the collective knows how to do it, the collective can improve upon it and make it better and add to it. And I think that's the end goal. Like that's why Linux is all over the place. It was free, it was given, and you had this huge collective that did things. And then you have people like Google that turned Linux into Android. And now Microsoft uses Linux. I think Linux is in the Microsoft like network, there's more Linux servers than there are Microsoft like Windows servers. It's just the sad truth. When the collective is bigger and the collective is intelligence and the willingness to improve said piece of work, the better it is. Money is the driving force for a lot of things, but sometimes the quest for knowledge is greater than money. Like that's how I approach these things. Like the quest for knowledge, the quest for answers is more important for money. Like when I'm unemployed and I'm looking for work, and people ask me like, how much do you want per hour? Or like how much I want. I say I'm looking for X amount, but that doesn't necessarily make my decision. It's like it depends on the work. If the work I'm gonna do is fun and I'm going to learn something new, that's more important than the monetary value that I get doing the work for you. Because, you're going to pay me to do the work, but you have to give me work that's worth my time. You know, I don't know if that sounds like a prima donna type of thing, but it's kind of like, it's like I scratch your back, but you have to scratch my back kind of thing. So you give me money to do work for you, but you have to give me work that makes it worth for me to get out of bed and to do. You know, like this stuff, I stay up till like 2 or 3 in the morning doing this. You know, it's like I get half the time I only get like 3 or 4 hours of sleep a night. You know, and I'm run ragged half my week. But that's the thing. It's like if the work is worth it, you know, you sacrifice other things for it. Now I'm not like a workaholic or anything, but like I said, to me it's the pursuit of knowledge, and that's why I'm making one of these videos. And like this subject to me is something I really love, and I wanted to do it, and I'm finally happy being able to be smart enough to do it. And I feel like there's a lot of people out there that feel like how I used to feel, like, oh, I'm not smart enough to do this. This is like way above anything I'm ever possible. And it's like I felt like that for years. I'm almost 40 years old, man. At 31 years old, my doctor told me I might be dead by the time I'm 40. You know, because of some health problems I had. You know, and I think that changed my outlook on life. It's like, screw it, man. Just because you feel like you're not good enough doesn't mean you're not. You know, just do it. Just effing do it. You know. By the way, even though I'm 30 years old, I'm not gonna die at 40 anymore. I took care of myself. I exercise. I eat healthy now, and I've tons of improvement. My doctor says I might live to be 80 as long as I don't get hit by a car or I hit a nasty disease or something. But you know, it's a shame that it's a shame for me, and maybe it's a shame for other people that they have to hit rock bottom before they change their outlook on life, or to take chances, or to just try things that they're afraid of. So, man, it's like this video is about curves and math, and I'm ending this with like life lessons. I don't know why. I guess it just shows you how passionate I am about this, but. So whatever. So open source, I want you guys to learn this. I want you guys to improve. I got 2 more legs to go. I got a piston leg, and then I got an animal leg. So like 3 bones. So this way, if you want to do like the hind leg of a dog or a cat, or like some of those animals that have like 3 bones, and like they have like these tiny little toes that they walk on. I got that. That's the final bone. That's the final IK solver I put together. And like I said, the arc, the arc, the piston, and the 3 bone ones, like you can't find online. No one can tell you how to do it. Like I searched, so I'm really happy that I managed to figure it out, and I'm gonna give it to you guys for free. Because like I said, it's the collective. If the collective knows how to do it, we can improve upon it, and we can make more cool stuff. And that is the point of fun with WebGL 2.0. That is the whole point of this. Else I would not waste my time and just put this online and try to sell it for money. Because it's not, like I said, it's not about money. I want to improve this, and I know my limitations, and I know that the collective aren't as limited as I am. So I help you, you help me, and we're all better for it at the end. And like I said, I also want to thank the new Patreon. Thank you very much. He gave me like more than $1, so I really appreciate it. Thank you so much. I really do. I don't want to announce your name just in case, you know, privacy things. But like I said, thank you very much. You did a nice solid, and I hope my videos help you. Hope the new code and the new solvers is well worth the tip you gave me. So thanks a lot. Again, like the usual BS, like and subscribe helps the channel. I still need about 2,000 more hours of views before I can monetize my videos. But until then, whatever. Right? Who cares? So yeah, see you guys at the next video.